All right, let's take a look at the Unit 3 review. Number 1 says, draw an example of a molecule where oxygen is not the most electronegative atom, and then one where it is the most electronegative atom. Label the partial charges. So, oxygen has a pretty high electronegativity. There's actually only one element that has a greater electronegativity, and that's fluorine. So, when we do this example, we got to first figure out how many fluorines would bond with oxygen, which has 2 lonely electrons. And we have seen this example a few times. So it looks like 2 fluorines makes this perfect compound. Since fluorine has a bigger number for its electronegativity than oxygen, we draw 2 arrows pointing at the fluorines, which give them a partial negative charge because they're stealing more than their fair share of that electron cloud. That leaves the oxygen partially positive. An example of where oxygen is more electronegative is in H2O. It's 3.44 still, and hydrogen's electronegativity value is only 2.1. So here the arrows point at the oxygen, giving it the partial negative, and each of the hydrogens gets a partial positive. Number 2 says, for each of these bonds, label which side has the partial positive and which side has the partial negative. Well, for letter A, we just did that one. The hydrogen gets the partially positive. For carbon and fluorine, you may need to reference your electronegativity chart to look at the values, but whichever one has the bigger number, that side gets the partial negative because it's stealing electron cloud. O and F, we just did this one as well. The oxygen in this case is partially positive. How about between oxygen, 3.44, and phosphorus? Phosphorus is 2.19. That means in this example the oxygen is partially negative. How about between oxygen and carbon? Oxygen is again the most electronegative, so it gets the partial negative. And between nitrogen 3.04 and hydrogen 2.1, that nitrogen is partially negative. Number 3, for each of the molecules below, which one would be harder to boil? Explain. Well, for letter A, it's all carbon and hydrogen bonds. That's a tie, 2.55 and 2.1. The difference between those numbers is only 0.45. If it's not 0.5 or greater, then there's no polar bond. So this would be a non-polar molecule. Same thing with C8H18. So if I drew this all out, it continues, it would all be hydrogens and carbons. So this is also nonpolar. So now we've got to think which one would be more difficult to boil. And the answer is definitely going to be the larger one, because if you can imagine 2 of these lined up side by side, that random motion of electrons causes some attraction, and the bigger the molecule is, the stronger that dispersion force will be. So even though it's a tie between dispersion and dispersion in this example, the bigger one will be harder to boil, which makes sense. It would be more difficult to turn that one into a gas and break that intermolecular force between the molecules. How about between H2O and H2S? Well, oxygen has that value of 3.44, hydrogen 2.1. That's a dramatic difference, causing there to be partial charges, the oxygen having a partial negative and these hydrogens having partial positives. For the sulfur in the hydrogens, sulfur's value is 2.58 and the hydrogen is 2.1. So that's only a difference of 0.48. So this would fall into the nonpolar category. So now you're talking about hydrogen bonding forces versus dispersion forces. So the one that would have the higher boiling point would definitely be the one with the stronger forces between them, because if you line up some water molecules, this intermolecular force between them is very strong. And that's because of those partial charges attracting these guys together. So it's going to require more energy to break that. For letter E, we've got HCN and CO2. Nitrogen's value is 3.04. Carbon's is 2.55. That's a difference of 0.49. Oops, 0.49. So that's really close to that 0.5. So we're going to call this at least slightly polar. So we've got a partial negative on that nitrogen, leaving the carbon slightly partially positive. It's definitely more polar than the carbon dioxide, which is linear, and so those poles to the right and left cancel each other out. So the carbon dioxide would have dispersion forces, very weak forces between molecules, while the HCN would be somewhere between dispersion and dipole-dipole. Remember, it's not black and white. All of these things are on a continuum. So in this situation, HCN would be more difficult to boil because those molecules are slightly sticky, more attracting each other than the carbon dioxide molecules. Draw a picture of how 3 HCl molecules might align themselves and explain. Well, we've got a big difference here. That chlorine is going to have a partial negative and that hydrogen a partial positive. So when 3 of these line up, we want to put the partial positives next to the partial negatives. So they would definitely line up with chlorines facing the hydrogens. And for the last table, we've got to draw some structures and name their shapes, as well as their polarity and what the strongest intermolecular force present would be. So I'm going to bond everything once, and then I see there's still 2 sets of lonely electrons. So this is a linear molecule around each of the carbons. To figure out if it's polar or nonpolar, again, we check the electronegativity chart and we see are there any bonds that have a difference of 0.5 or greater. And in this case, everything is a tie, so this would be nonpolar. Using our handy-dandy flowchart, if something's nonpolar, it's definitely going to have the weakest forces between those molecules. In this case, dispersion. For CH3OH, I want to draw it representing this having a bent shape. Around the carbon is a tetrahedral, and around this OH is a bent shape. Now carbon's 2.55, and we know that's a tie with the hydrogens. Hydrogen's 2.1, but here we've got a greedy atom. That oxygen is pulling electron cloud away from both the carbon and the hydrogen. So that oxygen has a partial negative, and these hydrogens and carbons have partial positives. So this is definitely polar. Anytime you have a molecule that results in partial charges, it's polar. So now we go and say, okay, does it have an H directly bonded to an F, an O, or an N? Yes, it does. That means that this molecule, when it's with a bunch of other molecules of its type, is going to have very strong intermolecular forces between the molecules, hydrogen bonding forces. NH3 is going to be very similar. It's a little less complicated because we just have one central atom with a pyramidal shape. Nitrogen is much more electronegative than those hydrogens, so it will steal electron cloud and leave those hydrogens partially positive. This is definitely polar. And like the last one, it does have an H directly bonded to an F, an O, or an N, so it's going to be another one with the H bonding strong forces. Carbon dioxide we saw in our other example. just to be clear, because there's these strong, greedy atoms, but in a linear shape, the opposite poles cancel each other out. So that leaves this molecule nonpolar. And we know that nonpolar things have the weakest forces between them, holding them together. That's why they're often gases. N2 ends up being a triple bond between two nitrogens. So all it can be is linear and nonpolar because there's nothing that's winning there. So again, we've got dispersion forces. And our last one is very similar to, what was it, the CH3OH. It's just got an extra carbon. So now we've got two tetrahedrals around these carbons, and we still have one bent shape. This is definitely polar, again, because the oxygen is stealing electron cloud away from the hydrogen and the carbon. So just like that other one, this one is going to have hydrogen bonding forces. Of all the molecules in the table above, which do you think would be the hardest to boil, and why? Use Google to see if you were correct. So we know it's got to be between the CH3OH, the NH3, and the C2H5OH, because those all have the strongest forces between them. Then, knowing that all of these have the hydrogen bonding forces, I would choose the largest one to guess that that would have the highest boiling point. So I can check Google. I happen to know that the names of these are methanol, ethanol, and ammonia. So I can do a little research and check my answer here. Boiling point, oops, ammonia, -28 Fahrenheit. Let's check methanol, 148.5 Fahrenheit, and let's check ethanol, 173. So yay, we were right.